All right, so on to 9.4 here for AP Calculus. So what was the point of all this series stuff? How did it relate to derivatives and integrals? Well, that's what we're going to try and get into today. So we're going to take a look at what a Taylor polynomial is, or just what's the idea behind a Taylor polynomial. All right, so first up, what we want to do is we want to create a polynomial that matches the function value at a point, but then matches the derivative at that same point, and matches the second derivative at that same point, and so on. Right? And we would think that if we kept doing this so it would match every single derivative at that point, that it would be just about the exact same function. All right? Or it would be very close to it at that point anyways. All right? So if we look for a first degree polynomial approximation of e to the x near x equals 0, then what we would do is, well, we'd want to know what's the actual function value at 0. It's just 1. What's the derivative value at 0? Also just 1. So we can make a polynomial out of this with these two coefficients so that when we take the derivatives, or if we plug in the original value, it will match. And that polynomial is just 1 plus 1x, right? This works as this coefficient, this works as the coefficient here. That way, if I plug in 0, the actual function value, I'll get 1. And if I plug in, or if I take the derivative and plug in 0, I'm also going to get 1. So it matches for the first two derivatives, all right? Which is nice because it's a lot easier to evaluate 1 plus x than it is to evaluate e to the x if you don't have a calculator. All right, so that's really what's happening here. So if we look, the black graph here is the graph of e to the x. And here is that approximating function that we just found, this polynomial, this first degree polynomial 1 plus x. So if you notice, they match right here at this function value. So if we plug in 0, we get the same function value. And it's a tangent line, right? So it has the same slope right there. But if we went to like the second derivative or the third derivative or whatever, it wouldn't match anymore. All right, so what we can do is we can keep doing this process more and more, like more derivatives, and we can come up with more terms. All right, but the more terms get a little bit funkier each time. Right? Because the actual polynomial we want to create would look like this. Right? So if we just plug in 0, sure, p sub 3, this is the third degree, so we say p sub 3, third degree. So p sub 0 would definitely just be a sub 0. But if we took its first derivative and plugged in 0, then we bring down this 2 here, we bring down the 3 here, and we get those two terms. But if we plug in 0, those terms are still going to go away, and we just get a sub 1. All right, but now if we take another derivative, the second derivative, we'll have 2a2 left. This x will go away. And we bring down the 2 here, so we have 3 times 2, a3 times x. And if we plug in 0 here, we get 2 times a2. And then if we take a third derivative, all that's going to be left is this coefficient here. And if we plug in 0, we get exactly that coefficient. So you can see what's happening. Like if it was a fourth degree, it'd be 4 times 3 times 2, a sub 4. And fifth degree would be 5 times 4 times 3 times 2, a sub 5. In other words, you're getting exactly n factorial in front of a sub n is what's happening. All right, so what ends up happening here is, well, we're going to divide by that n factorial each time. All right, so we'll keep working with e. So all the derivatives are e or just e to the x, so it's really nice. So if we plug in 0 for each one, we're going to get 1 for every single one of them. Again, real nice. So that means a sub 0 is 1, and a sub 1 is 1, just like we found. But 2 times a2 would be 1. So a2 would end up dividing by that 2, and we get 1 over 2. And 2 times 3, a sub 3 equals 1. So we divide by that, and we get 1 over 6. And we put that all together, and this is the polynomial we end up getting. All right. Can you think about what the next term would be? Well, it definitely would be plus. It definitely would have an x to the fourth. And it'd be 1 over, so this was 3 factorial. The next one would be 4 factorial, so it should be 1 over 24. All right, and the next one should be 1 over 120 x to the fifth, and so on. Which means these terms are getting really small. All right, so that does help us when we want to plug into our polynomial. So that's the idea that we're working with here. And if we look at the graph of this p sub x, this guy, I mean, look at it, like from here to about here, like they are matched almost perfectly. Right? So from like -1 to about like maybe 1.5, they are almost exactly the same graph. Like you can hardly even see the blue graph for most of that. So it's a really good fit for a long stretch of the graph. And even after here, like they're both still going up pretty close to each other. After here, though, this one's kind of going down and this one's kind of going up. So the concavity changes as we get farther away. But notice they have the same value. So they have the same function value here. They have the same slope. They also have the same concavity. All right. So, and we'd also be matching on whatever the third derivative is, the jerk. They'd have the same jerk there too. All right. So the more derivatives we make and the more coefficients we make here, the longer and longer this function, this polynomial function we make is going to match this exponential function. All right. And we can do this with any function. So that's the key here. That's what these Taylor polynomials are. We can do it at any function. And this one's centered at 0. We could center it at any point. Like we could match this at x equals 3, and we could just keep plugging in 3. And that the coefficients wouldn't be as pretty, but it could work. We could do that. And we can do that any function, anywhere. All right, so that's the general idea behind Taylor polynomials. All right, in the next presentation, we'll come back and we'll find several Taylor polynomials.